Thank you for tuning into this presentation and greetings from Florida. My name is Nick Heath. I'm a scientist with AER, and today I'm going to be discussing the use of CRIS ammonia observations to improve ammonia emissions and then ultimately decision making on PM 2.5. So this is really a collaborative effort across many divisions at AER and with Environment and Climate Change Canada. And all of the names of the people listed here actually did most of this work here, and so they deserve all the credit. This project was really motivated by the fact that we can observe ammonia from space using the Cross-Track Infrared Spectrometer Instrument, or CRIS. And so what this plot is showing is shaded is the CRIS observations averaged over April to September 2013, and then the corresponding AMON surface network observations over that same time period. And so what you can see is that CRIS is able to capture the general trends, general gradients, and hotspots that AMON is seeing at the surface, and then also start to provide more information. We're seeing additional regions of enhanced ammonia and regions we might not have seen with just the point observation. So this is really showing the usefulness of having a satellite where we can see a broader area. Further evaluations from Environment and Climate Change Canada looking at the correlation among the CRIS surface observations and AMON surface observations over a 4-year period from 2012 to 2015 showed good correlation. So this is just a couple examples from Stockton, Illinois and Fort Collins, Colorado, showing that we're getting correlations anywhere from about 0.7 to about 0.8. And given the pretty significant differences in sampling, so AMON is about a 2-week average, whereas CRIS is a once daily overpass. AMON is a single point, whereas the CRIS instrument is about a 14-kilometer footprint. And the fact that CRIS is looking through the vertical, so it's actually weighted most heavily between about 900 and 700 hectopascals, whereas the AMON network is right near the surface. These are some pretty big differences. So to still see this good of correlations is very encouraging and gives us hope that we could use this data for air quality modeling purposes. So that gets to the overall goal of this project. So what we're aiming to do is take these CRIS NH3 retrievals and provide improved emissions inventories of ammonia to you all, to the air quality modeling community, and hopefully be able to give you the data so that you can improve the emissions for whatever your application is and whichever air quality modeling you're using. So here's just kind of an overview flow chart of how we're going about doing that. So all of this is being done on Amazon Web Services, so on the cloud. And it all kind of starts with our AQCAS pre-processing system. So this is something that was developed at AER, where we can run WRF and all of the, MSIP, ICON, Beacon, all of the pre-processors for CMAC. Then for this application, we're running 2 versions of CMAC, which I'll discuss on the next slide, but a baseline and a perturbed. That output gets put into this emission scaling factor calculation, where it is informed by the CRIS retrievals and then the difference between these two. And then once we have the updated emissions, that goes into an optimized CMAC. So CMAC is rerun now with the updated emissions. And then we can iterate over that loop as many times as needed until this is no longer adding value, until we get some sort of convergence toward the final emissions values. Then, of course, we want to evaluate and look at different surface observations and, when available, aircraft data to make sure that this process is, in fact, improving the model results. And then in this right box here is where the users come in. This is where you would come in. You could go to a website, put in the model you're running, the time frame, and then the grid you're running over, and we would provide you updated emissions for that time period and that grid. Now, it's either going to be that we output it in model-ready files, or we just provide you with the raw data in a netcdf format, and also the accompanying script, whether it be Python or Fortran code or something, for you to regrid it yourself. They would already be ready to go, and you would just run it for your particular model. So that's a general overview of the process. So what I want to look at next is this portion here, the more sciencey portion, where we're actually, how are we going about getting these updated emissions? So it all starts with this paper, Lamsel et al. 2011, and several others that have been published since. And it's this idea of a mass balance finite difference approach for top-down emissions inversions. So the first thing we do is we run a baseline CMAC, and then we run the exact same CMAC with the ammonia emissions perturbed by 20%. And then having these two runs, we can calculate this beta factor, which is shown in the equation here. And essentially what this beta is representing is a sensitivity of how do the concentrations, which are shown as this omega, change as a result in changing emissions. So once we have that beta, that sensitivity factor, that gets plugged into this emissions factor calculation, where now we're using the concentrations from CRIS and the concentrations from the baseline CMAC together with that sensitivity factor to weight the a priori emissions and come up with this final emissions data. So then once we have these updated emissions, we plug that back into CMAC, and then we repeat. And we can do this, like I mentioned, as many times as needed until these steps aren't adding any value. So we originally did this for the CMAS campaign in June 2013. So in the top left, this is the baseline CMAC we ran. And this, what we're seeing is the monthly averaged CMAC ammonia minus the monthly average CRIS ammonia. So areas of red are showing over prediction, and then areas of cooler colors are showing under prediction compared to CRIS. So after just one step of that iteration, this is what the results look like. So you can see it is pulling things in the right direction. It starts to bring down, for example, over in northern Alabama and northern Georgia here, we see some of those over predictions are being reduced. So it's taking things in the right direction. And then, so that's, of course, just doing what it's supposed to do, getting closer to CRIS, but we wanted to validate that independently. So this was measurements taken during the CMAS campaign from the aircraft. And so this is the same thing, just showing the difference between the model and the observation. And in this case, we see that where it was CRIS was saying we were over predicting, the aircraft was also saying that CMAC was over predicting. And then when we ran the inversion method, we see that over prediction is improved, and in general, it looks better when compared to the aircraft observations. So this is very encouraging, saying that this approach seems to be working, and even when validated against independent data, it's adding value. However, we found that we could do better even. So some closure studies that were done within AER found that the total column is a better metric than the surface concentration. So in those, the plots I showed previously, that was using surface concentration for the inversion. And what this closure study found was that the column is actually a better metric for that, because essentially what happened is that we were getting this gap when we're using the surface concentration, where CRIS was not able to fully resolve the whole spectrum of both modeled and observed ammonia concentrations. And so when the a priori profile was moderately polluted, it was clumping the values towards lower concentrations. And when the a priori was in a polluted profile, it was clumping it toward higher values. So we found that when we switched to the total column, we were able to better resolve across these two. There wasn't such a gap between the a priori choice and a better resolve a broader range of concentrations. And so clearly this looks like a much better approach for if we're going to do a model to satellite comparison, this would be the better metric to use. So that was the next part of the project, and kind of the new stuff that we're showing here is that we went back and ran this exact same process, but now the omega is total column rather than just surface concentration. And because we're doing this in a system where we want to make this automated, we decided to start kind of from scratch and see if we could demonstrate that the system works from start to finish. So we just chose a random month of 2015, June 2015. and decided to do a brand new simulation from there. So we ran WRF version 3.8. These are the settings: the YSU PBL scheme, the NOAA land surface model, our TMG radiation scheme, and the Grell-Freitas cumulus scheme. For CMAC, we ran version 5.2, and we did it over the entire CONUS here, so the standard 12-kilometer CONUS domain, rather than just over the southeast, as you saw in that first demonstration. We ran CB05, AE6 aerosols, and then we were using the NEI 2011 emissions platform. So here is the first results from what that looked like from this new prototype. So on the top is the CRIS average total column over all of June 2015, and then on the bottom is the accompanying CMAC average column. So this is a CRIS simulation. So essentially this is what CRIS would have seen in the CMAC atmosphere. And so as you can see, it's it's under predicting across the board essentially. So when we ran the inversion, as you might expect, the emissions were scaled up pretty dramatically. So after one iteration of that inversion process, this was the baseline, and this is the updated emissions. This is just one snapshot halfway through the month. But as you can see, pretty much everywhere the emissions are being scaled upward, and this is on a log scale, so pretty dramatically in some areas and not so much in others, but across the board almost an increase. When we now go back to this comparison with CRIS, here was the original, and here's the update. So I'll just kind of go back and forth once or twice. So you can see pretty much as we might expect, it's increasing ammonia across all of the CONUS and comparing much better with CRIS now. Of course, this is only one iteration, and like I said, it could be now over doing it in some areas, and then doing another iteration would bring that back, and the goal would be to kind of go back and forth until that finds its balance and finds the correct or the best estimate of the emissions. And so in any case, this is encouraging to start from a fresh case and see that the process is working using the total column as the metric rather than just the surface concentration, and therefore we think this is going to be a more a better metric for doing this inversion process. So the next steps for us is that we want to expand the modeling domain to more portions of North America. We want to cover all of Canada and then Alaska. We're also, it's not shown here, but we are working on adding in the bidirectional ammonia flux. So in the 2015 example I showed, we did not use the bidirectional ammonia flux, but we've been working on that, and that's almost fully incorporated into the system. So that will be part of it. And then of course we want to develop the software for the regridding so that when you download it, you have an option to regrid it to the model of your choice and for your domain and time period. And then ultimately, the final step is just to make sure that the automated process on AWS is working as expected and it's efficient and fast so that it allows you all to get the data you need when you need it. So to summarize, the overall goal of this project was to improve emission inventories of NH3 using the CRIS ammonia observations and using an inversion approach. Our closure study found that the best metric was the total column rather than the surface concentration for doing these CMAC to CRIS comparisons. And then we were able to run a prototype for June of 2015 across the entire CONUS and found that the NH3 emissions are dramatically underestimated in CMAC. Of course, we didn't do any further validation, so that's going to take that's additional work we're working on. But the first cut at it suggests that we're dramatically underestimating ammonia. So that's all I have, and I again appreciate your time and look forward to questions. Thank you.